Got your exam this Friday today. All the details for the rest of the week and for the beginning of the week are right here in Piazza. If you have any questions, go ahead and just send you there. But otherwise today, we're doing as many exercises as you want here, right? This is a midterm from 2000, so about two years ago. Obviously, we're not going to do all of it because some of it involves arrays, which we have not gotten to yet. But we can do at least the first part here, right? Where you've got this medical application where you need to estimate the body surface area of a patient. And so, it's really, you have to estimate it, of course, because you can't, people are not rigid cylinders or capsules or whatever, right? So there are three formulas from the literature that you can use to estimate the body surface area in, of course, square meters, that's area, based on a patient's weight and height, that's kilograms, and in centimeters. And the Devoy formula uses a square root. Haycock formula uses this combination along with powers. And then the Boyd formula has the same combination with powers, but it also incorporates this natural logarithm over here, the natural log. So we want to write a program that reads in a patient's height and weight as command line arguments, right? In other words, non-interactively. And then produces a table that looks like this: 76.5 kilograms and 175.25 centimeters tall. Means that you have about a little shy of 2 square meters of body surface area. Right? So, C or Java? C? Okay. C155H, there we go. Let's go ahead and create a file here called bsa.c because that's what the instructions tell you to do. Right? Put everything into a file named BSA. Okay. All right. Is this big enough for everyone? Let's see. A little bit bigger. There we go. Now it's fine. All right. So full program here. What do I start out with? An author header. Right. There I am. Date. Sure. All right. Email if you want. Whatever. Purpose of the program. This program computes a patient's body surface area, BSA, based on three formulas, right? The Devoy formula, the Haycock formula, and what was it? The Boyd formula, right? And if this were a full documentation, I might even put in a web link or something to wherever the hell I got those when I wrote this exam, right? But this is good enough for now, right? Given the weight, the patient's weight, and in kilograms, and height in centimeters. Right? There, good enough. Obviously, I'm going to want to bring some libraries into the mix here. Always include the standard library, stdlib.h. Probably going to be doing input-output, right? So include stdio.h. What else am I probably going to be doing? Math. Include math.h. Right? Int main, int argc, char, argv. Again, you'll have 15 hours here, so you don't need to come prepared with boilerplate like this. But if this were a timed exam or something like that, I would come with a boilerplate main at least, right? But you're not going to need it because you have 15 hours, right? All right, so if I'm accepting command line arguments, I better be checking to make sure that I have the correct number of command line arguments. And I can do that by checking argc. If that's not equal to, I expect height and weight, only 2 command line arguments. Nope, 3. Why? Because of that first command line argument in C, which is the executable file name. Printf, provide a height in kilo, or provide, let's go weight and then height. weight, kilogram, and height in centimeters. And then we'll exit on them. Because there's not much we can do. If they don't give us input, we're done. Right? Otherwise, if they do give us input, we can go ahead and record that. Weight is equal to argv sub 1. Is that correct? That is a string. How do I convert a string into an alphanumeric string into a double A to F? Right. There's weight, height, copy, paste. Hopefully I don't get myself into trouble. Right. Is this correct? Nope. Why? That's an integer. Right. That 175.25 centimeters will end up being just 175 centimeters, and all of our numbers will be wrong. Let's do some rudimentary checks here. Are all heights and weights valid? What's going to happen with our math here if we have, say, negative weight? The Devoy formula, what's going to happen? Negative weight plus, positive height. Imaginary numbers, right? Yep. What about that Boyd formula? Any failure there? Natural log is defined everywhere. Nope, not at 0. What happens at 0? Negative infinity. All right, so we are going to say that anything that is not positive is wrong. If the weight is less than or equal to 0, we'll go ahead and print an error message. Weight cannot be, or weight must be positive. And 1. And we can exit here too, right? You gave us bad input, we're done. We could also check, else, if height is negative, then the height must be positive. Good. All right. Otherwise, we're going to want to output the first part of this table here. Right? I'm going to go ahead and cut and paste that here so that I can just match it exactly, printf. Here's the patient, right? They are printf weight is going to end up being, if you want it accurate out to 1 decimal place, how would I end up doing that? Percent 0.1f kilograms, and then end the line, and I will echo out, back out the weight. Printf height, and if I'm accurate out to 2 decimal places there, what should it be? 0.2f centimeters, right? And that's height. Line that up. There we go. And then I can print out the header of that table, right? Formula. I could even make it really fancy here with like some vertical lines. Yeah, let's make it really fancy. Formula, and then what was the other header? BSA. There it is. BSA in meters squared, and the line. You can get as fancy as you want with 15 hours. Right? You can go ahead and make this into some a really cool ASCII text art of some sort. There we go. That's good enough. All right. And then, oh, here, when we actually cut this off, we'll go ahead and go like this. And then plus. There we go. And that's our separation, right? You can get real fancy. Don't get fancy. Right? Don't waste your time unless you really want to. Right? I had an excellent student one time in the honors section. They completely finished their exam. This is back when I gave written exams. So this is over almost 10 years ago. And they got done really, really quickly. And so instead of leaving like they could have, they spent the next half hour drawing this very, very elaborate dragon on the front page of the exam. Very cool, right? But make sure that you get the exam done before you start drawing your dragons, right? All right, there's the Devoy formula. I'm going to put it over here so that we can view it off to the side. This is where 2 screens is an absolute necessity for any developer. 3 screens is even better, although it's kind of weird then because now 4 screens, now that's a symmetry, right? Always make sure that there's an even number of screens there. All right, so let's go ahead and compute these things. Should I just call it BSA? No, we got 3 BSAs here, right? So I'll name it after the formula, the Devoy formula, BSA. Right? That's going to be square root of height times weight divided by 3,600. There. Now think about that. Are there going to be integer truncation issues here? No, because what height and weight are doubles. Is there going to be a numerator issue here? Mathematically, I don't think so, but we can go ahead and make it nicer looking, just to be sure. Double, what's the other one? Haycock, BSA. And that's going to be this thing right here. And I'm going to cut and paste because I want those numbers, but look what happens when I cut and paste, say, from a PDF. So is that going to work? Times. Nope. In fact, those aren't even valid ASCII text characters. Those are special characters, Unicode characters that were formatted in the PDF. All right. So replace those. Right? Replace that. Right? And it's not it's not h times that. It is h raised to that power. Right? Height raised to that power. That's not correct. Some programming languages, Python, allow you to do something like this. Right? That's the exponent. C does not allow you to do that. Instead, what do we have to do? The power function. Right? And pow of weight. There you go. Okay. Good. The numbers got copied. There's no Unicode there. And then finally, the, what was it? Documentation tells me Boyd BSA is equal to, once again, I'm going to go ahead and cut and paste this because I don't want to mess up the numbers. It's not going to let me. Fine. 0.0333 times pow of height, 0.03 times pow of weight raised to the power, and then there's, help me with my copying here, 6157 minus 0.00816. 474, right, times natural log of weight. Is that the natural log in C? Nope. What's the natural log in C? It's log. Right. All of my parentheses, I think, are correct. And now let's do the average, right? Because we also have to report the average of all those things. Average BSA is equal to the first one plus the second one plus the third one. Divided by 3.0, you could go ahead and get away with 3 there, right? Because there's no integer truncation issue here either. Right? And now let's go ahead and print each one of those out. Printf, Devoy, right? Fancy. Percent, how many digits? I think it's just the default 6 here. And the line, Devoy, BSA. There we go. And then 3 more. This is Haycock. Nice lines up. This is Boyd. Put in some extra spaces so that lines up. And then this is the average. If you want to, you can go ahead and put that down below. That's going to be a really fancy table, right? And these should be Haycock, Boyd, and average. All right. How do I compile this? Is it enough to do just this? Predict. Nope. If I'm using math, what should I bring in? -lm. If I'm making sure that I'm doing everything correctly, I should also use the wall flag so that it tells me if there's anything that I missed that it can catch. Ah, great. Perfect. If I don't give it any command line arguments, we get that error that we expected. If we give it negative values, then we get that those error messages that we expected. And if we give it the values in the handout, 76.5 and 175.25. There we go. Oops. We get the nice looking table that looks exactly like the one in the handout. All right? Any questions on that? Really quickly here, how do I translate this to Java? What's the only difference? Or what's going to be one of the very few differences? First of all, what should I name my class? It's in the handout, and so it tells you what to name it. But if I wanted to name it BSA, the name is discouraged. By convention, Java type names usually start with an uppercase letter. BSA is what we tell you to use. I could have had it also generate that main for me. Let's do that. No, here. I'm just going to cut and paste. There we go. All right. I don't use any includes. My main would actually go inside my class, right? So let's bring that up here. This program, yep, there we go. There's the main, except that we don't have this. What does our main look like in Java? Public, static, void. You can do int, I believe, but don't quote me on that. And then it doesn't take two arguments here. It takes string args. It takes an array of them. Args.length. Now here, are we expecting 3 command line arguments? We're expecting 2 because the first command line argument is not the executable file name. You wrote that up here, right? Okay. System.out.printf, or you can go with system.error. System.exit. Right? Now it's not args, it's argv, it's args, and it's not 1 and 2. It starts at 0 and 1. And I don't use A2F. I use double dot parse double. There we go. All right. What else? Well, system dot. Oops. System dot. System dot. System dot. I don't want to have to type all that crap. So what I'm going to do is I'm going to find printf and replace it with system.out.printf. Replace all. Close. Done. Except it will screw up this one up here where I prematurely did it. I should have done that as the first thing. Most of it's taken care of now with that one simple replace. There's no return statement here because the main in Java here is a void function. Don't return anything. Square root, it's math.square root. Likewise, math.pow, math.pow, and math.pow, and math.log. Ooh, I wonder, is that still the natural logarithm? How do we know? If I hover over it, it tells me. Returns the natural logarithm base e of a double value. We're good. There, almost done. Math.pow. All right. If I run it, of course, it's not going to give me any output because I can't give it command line arguments. How do I do that? Run configurations, arguments, 175.25, or no, 76.5 and 175.25. Apply that, run it, and you get that same exact table. Right. We just translated it to Java in less than 5 minutes. Right? Questions? No? All right. Let's see. No, this involves arrays. So let me go back to my repository over here. And we can go to last year. Unfortunately, I'm not going to have anything that's not a loop that... I don't want to do this one either. So this one is basically the exact same thing. Here are 3 formulas with basic input. Go ahead and compute these formulas with the output in a table, right? This deals with Pythagorean run expectations in baseball specifically, but this is actually a mathematical phenomenon in any sporting event. You can what you can do is you can say the goals scored, or in this case, the runs scored for and runs scored against, can actually predict how many wins you're going to, that you should have, right? And using these formulas. Right? And once you've got these formulas, then you can predict how many wins you should have, and then here are the actual number of wins, here are the actual number of losses, how much in error are these formulas. And it turns out, well, because the formulas were built from historic empirical data, they're pretty accurate. So the way that these things are actually used in practice are at the beginning of a season. Again, it doesn't have to be baseball. These formulas exist for any sport. You only need, say, 20 or 30 games into the season, or 5, 10, 15% of the season, and you can take their performance right there and predict what they're going to be like at the end of the season with pretty fair amount of accuracy. Now, there are, of course, outliers, and you can improve greatly, and then that changes all the statistics or whatever, but it's pretty sound. Right? Again, it's plug and chug kind of stuff. Right? If there's an equivalent of plug and chug in computer science or in programming, it's the simple input-output program. Here's some input, here's a formula, produce the output. Right? If we want some more practice on loops, though, let's see. Where's my book? Any questions? Or do we want to do this one? No? I'm not hearing any strong feelings anyway, one way or the other. Hey, there's a loan program. We did that. This one's nice. The rate of decay of a radioactive isotope is given in terms of its half-life. So if you don't like sports, surely you like science instead, right? Physics, right? So we've got a radioactive isotope, say, of strontium 90, right? And it has a half-life. Strontium 90 is a byproduct of nuclear reactions and also nuclear weapons, and it has a half-life of 28.9 years, meaning that if you have 10 kilograms of strontium 90 now, then 28.9 years later, you only have 5 kilograms of strontium. And the rest of it will have decayed into its decay products, uridium 90 and zirconium 90, which are also radioactive isotopes. Right? Eventually, that entire process, decay products until it finally gets into a stable isotope, and then it's no longer radioactive. Right? So write a program that takes the following input: the atomic number, which is an integer, the element name, the element symbol. In this case, those things are, what is strontium 90? What is strontium? Is it 90? 90 is the isotope number, right? It's 38, there it is. Strontium on the periodic table is 38. The element symbol, SR, H, the half-life of the element, and M, an initial mass in grams. Your program will then produce a table detailing the amount of the element that remains after each year until less than 50% of the original mass remains. This amount can be computed using the following formula. Mass times 1/2. Gee, I wonder why 1/2. That's why we call it the half-life, right? Does that game have anything to do with radioactive isotopes? Half-Life, the series? No, nobody plays that game. All right, fine. And then the years, the number of years that have elapsed, right? So if it's at 0, then this becomes 1, and you have your 10 kilograms of strontium 90. But otherwise, after 28.9 years, divided by the half-life here, the exponent becomes 1, in which case you have half as much as you originally had. Right? We're going to produce a table that looks something like this. Initially, we have 10 grams, say. Right? And then after the first year, you have 9.76 grams, right? Because that's what this formula says. Then it takes us 29 years because the half-life is 28.9 years, to get down below half of the original amount, right? At which point we have 4.99 grams. We don't necessarily have 5 grams, exactly half, because it's been a little over half the life, over the half-life. Well, since we started with C in the first version, let's go ahead and do Java for this one. New class Isotope. And yes, I want you to generate my main for me. I will skip the documentation here to do, but you definitely should do that. And now let's go ahead and accept those command line arguments, which were 1, 2, 3, 4, 5 things here, right? So to do some basic input checking. I'm also going to skip that because it's boilerplate, right? But you should not skip that in your exam, right? Otherwise, I'm just going to read in the inputs here, which were atomic number, atomic name, initial mass in grams, et cetera, right? So atomic number, it's an integer, right? If you look on your periodic table, they're all discrete, right? It's all integers there. Yeah?
If it doesn't say you have to use command line, can you do like user input?
It'll specify what we, but I mean, if you do user input interactive, and we told you command line, the scripts on the grader aren't typing into your program, right? This is going to be integer.parseInt of args0. Right? The next one, element name, would be a string, element name. And here I don't need to convert it, right? I can just go ahead and take arg sub 1, right? Because arg sub 1 is a string. The element symbol, string, element symbol is equal to arg sub 2. Strictly speaking, you don't need these as variables if you want to use args1, args2 when you actually go to print it out. But then you're using those mysterious variable names, and then you'll get them confused. Which one was which, right? But by using named variables like this, you don't get confused. Double half-life equals double.parseDouble of args3. And it is a double. Why? Because we've already seen an example where it's 28.9. Right? And M, an initial mass in grams. Certainly that should also be a double as well, because you could have 38.2 grams of plutonium or something, right? And I'll call this initial mass. Right? Is equal to double.parseDouble args. All right, I've got all my inputs here. I'm going to steal the table, at least the header of the table, right? And print that out, printf. Which Java am I using? Let's see if we can do something somewhat cool. Can I do this? String, what should I call this? Header is equal to this. Oh no, I can't do this. Can I? Come on. There we go. Now I can do it. All right, I'll explain what I'm doing here in a second. There. And percent 0.2f grams, say. There we go. So what did I do? 3 double quotes. What is that? It was something that was introduced in Java maybe 2-3 years, I forget what, but it's a multi-line string. Right? You couldn't do this with a single quote. String foo is equal to hello, this is going to the next line. You know, the Eclipse even tries to correct my mistake. Come on, I don't want it that way. There and there, right? You can't put a string on multiple lines, right? You can do it if you use a multi-line string, which is 3 quotes. So that's a newer feature of Java. I have no idea if it's supported by the Java version on the CSE server, which you have to compile to and run with, but you can try it. Right? I just want to make you aware that there are things that I'm not covering because, of course, you can't cover everything here. If I want to print out a string instead of just hard coding it to strontium, it'd be %s. This would be %d because it's an integer, and this would be %d. Actually, I'm not reading in that value, so I guess, am I? Name, symbol, this would be the symbol, %s. Atomic number, nope. Apparently I'm not reading in that 90 part. That'll be part of the name. It is actually part of the name. Right? Let's see if this works. System.out.print f, header, and then the arguments would be the element name, the atomic number, and then the element symbol, and then finally the initial mass. All right, let's see if this works. You have to run it once to see that that's not going to work, and then go to run configurations, arguments, strontium, right? Not strontium, 90. What else was it? What was the order of everything? Oh, atomic number first. Atomic number was 38. Strontium 90 is the name. SR is the symbol. Half-life was 28.9. And the initial mass was, I don't know, 10 kilograms or 10 grams. Are we good? Run that. Oh, nice. Any indentation is also generally ignored. Any leading white space. Otherwise, it would have printed way over here. So one of the nice things about this is if you have a big giant piece of text that you want printed, or then you can go ahead and format it exactly how you want within the code itself, and then just surround it with the 3 double quotes here without having to go to the next line, concatenate, go to the next line, concatenate, indent, whatever. Right? Okay, now I'm printing the header. Now let's get to the real meat of the problem here. I need a loop. I need a loop to execute for each year or until we get down below half of the original. So let me create a variable to capture the idea of the current mass. Double current mass. Initially, that's going to be the initial mass. Now, what kind of a loop do you want here? We could go with a for loop if you wanted to and go, the ceiling of the half-life to get to the next year that we know exactly half as much, right? We could say that int n num loops, num iterations is going to be the half-life, the ceiling of the half-life, right? Now there is no ceiling function, but there is a math.ceil function. So we all know what the ceiling is, right? It's not rounding because 3.5 rounded would actually go up, but 3.25 would round down. The ceiling says 3.25, that goes up to the next integer, right? And then we would force it to become an integer. That's the number of iterations you want, right? Is there another way? Just a while loop, right? While the current mass is greater than or equal to half of the original mass. That's why I made another variable so that I'm not changing that initial mass, right? Then go one more year. Now to do that, I'm going to have my year counter outside here. I'll initialize it to 1. I will system.out.print println, or printf, percent d for the year, and then percent, I don't know, 2f kilograms for the mass. Years, or year, and then current mass. There we go. Now if I just did this, of course the mass is unchanging, and I'll end up with in the first year I have 10 kilograms, in the first year I have 10 kilograms. Kill it. How do I update my values so that I have less? That's where the formula comes in. There's the initial mass, there's the number of years divided by the half-life, 1/2 raised. So current mass is equal to initial mass times 0.5 raised to the power of year divided by half-life. And I meant to do this, but of course remember you can't do that. What do we have to do? Math.pow of 5 raised to the year divided by the half-life. Now think about that. Are we going to have integer truncation issues there? Half-life is a double, year is a double. We're good. Okay. Is it correct to put it here, or is it correct to put it here? Which one? Well, let's try this one. I got everything correct, right? Yeah. All right. Still going. So, what's wrong? Yeah, go ahead. All right, so this is definitely, it should be in the first part, yes, right? Because year 1, I have 9.75. What else is wrong, though? Why I'm still going to be stuck in an infinite loop here. Yeah, go ahead.
You gotta do like current mass plus plus.
The mass is not increasing; it's always decreasing.
Or the year.
There you go, the year, right? Year plus plus. Why? Because I go on to the next year, the next year, the next year. And this, I think, should work. Right? Of course, it's not formatted nicely. If you want to, you go ahead and put this out to 10, and then it'll tab over a little bit. Right? Oh, but I want it left justified, so there you go. Oh, no, no, I don't want it left justified at all. I want this justified. There we go. And then you can play around with it and see if it aligns. So it did take us to 29 years, and it's 4.99. Take out your favorite radioactive isotope and try it out. Uranium, what is it, 235, has a half-life of several billion years. So you could put that in there and go for several billion years of iterations there. Hello from America. We got a hi from India message on YouTube. Right. Any questions? Again, what would you do to clean this up? Of course, everything that you put in the to-do here. Documentation, some basic input checking, right? The atomic number, you're not going to be able to look it up, but you can look up on the table and say, well, there is no atomic number 0. Atomic number 1 is what? Hydrogen, and then helium, and then other noble gases, stuff like that, whatever. And there is a maximum atomic number. I think we're up to what? 118, thank you. Wow. What about the actinides and lanthanides? Those go beyond that? Okay, I don't know either, right? But you could say, oh, if it's more than whatever the current scientific consensus is, then that's an error. Or you could future-proof it for new elements that are found. Element name, no. You couldn't really error check that, nor could you check the symbol unless you stored the entire periodic table in your program, or you loaded it up from a file and said, that's not a real element or something, right? Half-life, mass, you definitely could error check those. Half-life can be 0. That's a stable isotope that doesn't is not radioactive. The half-life cannot be negative. Something doesn't get more radioactive over time without some sort of a reaction, right? Initial mass, that could be 0 as well, and then it never changes, right? And although you would have to have a special check for that, but it can't be negative. All right. If you follow it along the entire time, then you're more than prepared for this Friday's exam. Don't sweat it. Go to your hack session tomorrow to get any hack points back that you're looking for. Then leisurely do your exam on Friday, and then have a good weekend.